Class 20, the lecture for Class 20. This is bolts 4. We're doing bolted joints that are carrying a moment. This is a sort of a basic kind of arrangement that we have where we have an eccentrically loaded bracket here that's bolted. In this case, it has 3 bolts. And we want to try to figure out what the loading on each bolt is going to be. So what we would do is we find a centroid, or a center of the bolt pattern. And we can tell right now that it's going to be right there at O. And what we do now is we're going to superimpose forces on the bolts. On top of the bolt pattern. And so that's not, instead of doing a free body diagram where we would find the reactions, we're actually going to use the equivalent forces that are going to be placed onto this bolt pattern. And we use vector addition to find what the bolt, that shear magnitude is, that force magnitude that's on the bolts. And there's many cases, some cases, where there's going to be a worst bolt, or maybe 2 of the worst bolts. And so we define something that we're going to call primary shear. A primary shear force. F prime. And that's going to be this force distributed along each bolt. So what we do is we divide for the primary shear. We say the primary shear is going to be the main force that's being applied divided by the number of bolts. And they're all going to be the same thing, at F prime. So in this case, they're going to be 1/3. And then we define secondary shear. A secondary shear force. F double prime. And F double prime is found by distributing the moment that is caused by this force being eccentric. And I might call some number, some parameter D, which is the distance from the bolt, from the force to the bolt pattern. And so it isn't a free body diagram, but it is going to be like we do put the this force on here, and so we apply, and we make that, you notice that moment's clockwise, which is the same direction as this force is making it go on. Well, that's so that we can take a look and see what kind of equivalent forces are going to be required that would generate this same moment that are going to be placed onto the bolts. And those equivalent forces are going to be this F N double prime is going to be equal to that moment times, and I'm going to come up with a parameter R. I'll explain what that is. I said A, but I meant Rn. Sorry. Rn, right? And that's going to be divided by RA squared plus RB squared plus RC squared Rn squared, right? So however many number of bolts there are, there's going to be this R. And that R is going to be defined by that bolt pattern, right? So right here in this case, this distance would be RB, the distance from the center to that bolt. And then this distance right here, this would be RA, right? And then RO would be 0 right here, but it would still come into the play, into the thing. That bolt doesn't do anything to the moment, if you can picture that. And so what we end up doing is we, let's see, we'll put on what that F would be. And in this case, we'd have an F double prime B right here, and then we'd have an F double prime A that would act right there. So the overall force that's acting onto this right here, and maybe I'll get rid of this thing, it's in my way, in green, would be FB, which is going to be equal to FB double prime plus F prime. And an equivalent thing here, we would have maybe this right here, because if we go positive or negative right here, we would say that FA is going to be FA double prime minus F prime. Or we could call it FA prime, but all the prime are the same. It's evenly distributed in terms of the shear load, right? So now what we found is that FB is going to be the worst case scenario. It's going to be the worst bolt. And so if one's going to break first, it's going to shear at bolt B first. And that's kind of like, if you take a step back and just look at this condition, it kind of makes sense, right? And if this thing was going to fail, like we were picturing it failing, let's draw the thing out right here. Let's picture this thing failing maybe. Let's picture it failing due to ripping the member out. Like, so this member can be ripped out, right? And so there could be a hole as this thing is coming down here, and then that part could rip out and that part could rip out as this force gets applied, right? Because he's going to be twisting around to this thing. And so like almost, picture what it would look like if that material wasn't there, right? It would, like, you know that it wouldn't be supported, right? If we went like this right here. And there was a pivot. As soon as you put a force right here, this bolt is slipping out, that bolt is slipping out, this thing wouldn't work, right? So that's the chunk of piece that would be coming out of this. And what we would do to try to evaluate that, we would take this force of there, and then we would take it against the areas that would end up like right in there. We'd also take, if we want to find the shear stress, we would take it across the bolt and take the F, and this would be the area of the bolt, and then we would get the bolt shear stress. So we could have other patterns, besides just those three in a row. Like in this case, we're going to have a bolt center that's kind of obvious by way of inspection. That's going to be right here. So now what we're going to do is we're going to find R's for each of these. So if I decided in here, I decided to call this one is going to be A, this one is B, this one is C, and D, right? And so this is RA, RB, RC, and RD, that distance, that diagonal distance from the bolt center right here. And so if we apply the moment that's going to be generated by this, it's going to create a moment where we have FA double prime. Let's try to draw this as best I can. FB double prime, FD double prime, FC double prime. Noting that these are all 90 degrees right here. And so now when we go to combine them, right? Well, no, I didn't put on the other. Let's see. Make sure we put on the single prime. So there's the F prime, F prime, and this guy might be kind of in the way. That letter might be in the kind of the way. Here you go, F prime right there, and then right here, F prime. We go to apply these, and we want to do like a parallelogram. Right here would actually be the FD, and similarly right here, right, FB, whoops, FB, and right in here, FC, and FA. So you get the idea, right? Where we would be able to, and by the way, because of some symmetry, I think FD and FB are going to be the same, and FC and FA end up being the same, just because of the way the thing works out. We might have one case here, so here's actually another case, and we know that the centroid is going to be, because it's a triangle, is going to be 2/3 of the way from the smaller part of the triangle and 2/3 of the way part of the other part of the triangle. So right here is going to be the centroid of the piece. So it's going to have an R here, and an R here, and an R here, right? And so all three of these are going to actually be different. So if these are A, B, and C, and we put in our, oops, meant to be red. Here's our F prime, and our F prime. And then we apply our perpendicular here. And all these magnitudes are going to be different right here, right? Because we would find, well, let's say, right in here, let me see, I got to write this thing in here. This RB right here, and here's RC, and here's RA, that we would have F B, let's say, is going to be equal to M, which is going to be M is going to be equal to F times D there. We would have M times RB divided by RA squared plus RB squared plus RC squared. And then, of course, that's double prime. And the F prime is just going to be F divided by 3 in this case. And we would add all those up, and we would be able to find what FB is going to be. Now, quite often, the easiest way to do this vector addition right here is to break the diagonal ones up into y components, right? So we have FBX, F double prime, and F double prime B y. So when we go to find FB, it's going to be the square root of F double prime BX squared, because it's the only one in the x direction, and then plus, and it depends when we do this on which bolt it is, whether the y's are agree or disagree with each other. This in this case would be FB y double prime plus F prime squared, and so then we'd be able to use that force to evaluate what the stresses are and possible failure modes because of that location. One thing that we might need to do if we have an odd bolt pattern is, that we can't just by inspection find, because this one was in the center, this one we know it's going to be in the 1/3 thing. Just like every other kind of centroid, we take a weighted average of the locations. If we were to say that the bolts have an area, we could take an area thing going on here. So we take the area I, some of the different individual areas, and multiply it by the distance in the x direction from some reference point, and we take it right here. But if all the bolts have the same area, it actually ends up just turning the sum of all the horizontal distances divided by the number of bolts will give us where the average location is. And the same thing up here, except that in the y direction, right? So that would give us end up giving us the same type of arrangement to try to figure out where the average location is, aka the center of the rotation that's going to take place. One of the possible failure modes that we have to look at when we're looking at this kind of situation that we might not have occurred before is also going to be for the moment, right? So the moment that's carried at the weakest spot right here. We also will want to look at that. So there's was looking for a good place to mention that as part of this in terms of the different failure modes that are possible. We want to try to discuss that. So let me talk a little bit about possible failure modes. Well, the first is going to be shear. Right? So shear failure is pretty likely because we have one bolt and we find what the maximum stress is going to be, no matter what the thing is going to be. Quite often it's near the front of this thing. Right here you can see that FB is the worst one in these cases. So shear of the bolt is a likely failure. And that's going to be tau, and is the F worst one divided by its cross-sectional area. And then if we want to evaluate it, make sure that we're comparing it to the yield, right, the shear yield, or 0.577 times the yield strength of the bolt. So that's one possible thing to do. Another is going to be a shear tear out. And that's very much dependent on where the bolt is located. And as I already mentioned down below, or up above, I guess, when we get down to here, like we could have, the hole here could have been sheared out through here. Right? But this one is more likely than this one because this one right here has the larger force for the tear out. But we can picture it by going out in both places. The truth is though that it isn't necessarily going to happen this way completely because it isn't going to rotate exactly that way, and but it's what we use as a safety factor as in essence to try to evaluate the likelihood of that. But that's going to be of the piece itself. So we have tau, worst bolt, and then 2 times the distance. A lot of times we were calling that distance to the edge was x, and then times the thickness of the thing, right? Because there was 2 different pathways for it to go. And then we also want to make sure we're taking the shear strength when we make the comparison, but now it's going to be the shear strength of the member, of the supporting member. We can also have bearing stress. Remember that bearing stress. So either making the hole bigger or putting a dent in the bolt. So and that's going to be obviously is going to be that F over dt right there. It's going to be for a single bolt because this force right here is for a single bolt. So that's d times t, not the derivative or the time fraction of t. And make sure that and that's going to be in compression. Make sure that we use the yield strength, the normal yield strength for either the bolt or the member. We could also have, now here's a different one. We could have bending stress. And the bending stress is going to come from this location right here, right? So it's going to be the cross-sectional area at the first bolt, right? So there's some chance that that's not the worst bolt, but it's going to be the place where you're going to have the most likelihood of bending, and it's going to be compression and tension onto these. And so you're going to have sigma is going to be mc over I, but that m is not the same m that we had up here, right? That m was going to be generated. This m is going, as I wrote, is going to be df, where this is d right here, right? So f times d is equal to m, whereas this m is going to be, and I'll just redraw this thing out here. Here's your force. It's going to be this distance right here, right? Because this other distance was, so this is the one that we care about right here, the one that's going to generate the moment. Because this other one was based on this, but we're concerned about that load that's taking place right here at that cross section, and that I is going to be missing the part of the bolt right there. So in this kind of cross section where the hole is centered across that cross section right there, we could just subtract out the little rectangle that would represents the hole. If it isn't, if we had perhaps this condition right here, where we're looking through this, and just the way this thing actually appears, it doesn't look like it's necessarily gonna fail right there. But just the what if right here, we notice that as a cross section. the bolt isn't centered, so we have to do a little bit more work. For one thing, the center, the neutral axis, will be shifted down. It isn't going to be the geometric center of the width. It's going to be, so we need to take the neutral axis about that. We also need to take the I about that. And so when we go to make the C, there's going to be two different C's in the MC over I, right? So the sigma equals MC over I. The I is going to require us to do a little bit more work because it's going to be about, like, maybe we call this the Z prime. That's going to be through the center of this cross section down here. And the I, you're going to need to use the parallel axis theorem in order to be able to find, to be able to shift where the center is. And you're going to actually have to use it. Well, is that true? Let me think about it. Oh, yeah, you have to use the parallel axis theorem twice, because you have to do one for the whole and one for shifting the thing down. And then once they share the same common axis, then you could subtract one from the other. So I don't want to write the thing out, but that's actually sort of a long thing to do. Actually, I'm not afraid to do it. So the centroid, so like if this is going to be the diameter right here, and let's call this the width right here, and of course that's the thickness right along here of the thing. We would have I is going to be equal to, I of the, let me see, I'll just write the thing out, BH cubed over 12. So it's TW cubed over 12, but now we have to subtract it out, the distance we're going to move it. And the distance we're going to move it is going to be, let's see, the Y distance from, I guess I'll take it from this baseline right here. That Y distance to the baseline is going to be W times T, right? That's the area, times W over 2. Right? And then we're going to subtract out the dt right here. And now we actually need another parameter. This distance right here is, I guess I'll call it, I don't know, I'll call it, not C, D, let's call it E. Right? So that's going to be that times, nope, I didn't mean to do that. I meant, let me make it this distance. That's going to be E, right? So that's going to be E, yeah, that's just E. Yeah, just times E. We don't need to do that. Yeah. E, and that's all going to be divided by, I guess, WT minus DT, right? So we could do a bunch of other stuff right there, but what I'm going to tell you is that we're going to, whatever this Y ends up being, right, because that's the sum of the areas times the distances to the reference thing, and that's going to be W. Now the distance from here that the thing has to move is going to end up being, so it's going to be minus whatever this area is. So I'll go with this area is equal to WT minus DT right here. No, I'm sorry. So let me take that back. No, I'm subtracting up here. I should be subtracting up here. I should really just abandon this, but that's okay. I did it anyway. I did it. So what we're going to do is take, where was I? Yeah, we'll take the area of the thing, right? So that's going to be the total area of the whole piece, and that total area is going to be WT, right? So that's the whole area of the big piece, and I'm adding it. Is that true? Yes, because it's going to be, it's going to get larger right here. So as I'm shifting the thing, and then I'm going to the distance that it's moving, I'm going to call that a distance Did I say C? I don't like using C right here. That I'm going to use DE and I'll use F right here. And so that distance that we end up moving from the thing is going to be F. Nope. Yeah, F squared. Yeah, so that's the distance F that we end up moving from the center to the new point. And that F, maybe we would say, was going to be W over 2 minus Y. Right? Because Y, I'm saying up here is where the new center is going to be. And that ends up shifting the thing down. All right. And then we're going to subtract out the diameter, the area moment of inertia there. That's going to be base times height squared, so it's going to be T times D cubed. I didn't say squared, I meant cubed. Minus right, 12. And now that's going to be plus. Now we need to shift where this guy is from his center down to this down to this new Y position right here, right? Where I'm calling this distance Y. Yeah. So that's going to be D times T times the shift that I made. So I actually it's going to be E minus Y, right? E minus Y, and that's squared. I probably should have done that a little bit more organized, and I'm thinking it out loud as I'm going through, and I don't know if it's going to help you any to do it, but it's I figured I'd just do it as while I was here. I'm glad I didn't do this during class time. It's a big distraction. But anyway, you want to do bending. That's the important thing that I was trying to get to. Bending, and is there any other possible, let's see, bending stress, and I think that's it. Okay, so we have the tear out, we got the shear, the bolt, that's probably the first one we go to. We got the bearing stress, we got the bending stress. I don't think any of the other ones are possible. And then I said I will do the examples in a separate video here, but I thought I would mention this kind of couple other scenarios that might be possible. In yeah, so I brought this up as a what if type of thing. Let me move this thing up a little bit, and I'll discard all that nonsense. And okay, so on one of the, I wonder how long my video is going to be on here. It's already 27 minutes. Darn. One of the projects I worked on an electric boat was on some propellers and propeller blades, and they were faced with a pressure wave that hit them, and we used an FEA model, and it returned some loads. We could pull off loads at these little links that represented bolts, but that's not exactly the right way to represent the bolts, because the part where the blade or whatever it was that is connected to the hub right there, it's squishy. We just learned that, right, from our previous class. These are preloaded, so it won't exactly, all those bolts will feel that. There's going to be a certain amount of interplay. And so we had to kind of come up with a way, or there was a certain logic that we would say that how is the load distributed in these bolts? So we had a couple. One way that often will get done is to take a look at this, and let's say we have this force, right? So, and here's the wall right here, and we'll say that it pivots right along this axis right here. So there's a pivoting thing that's taking place. Of course, we're greatly exaggerating this, but so this bolt right here is getting stretched, and this a lot, and this bolt here is getting stretched a little bit, right? So that's one way of doing it. We'll assume that the thing is distributed this way. Another way that we could do it is we could acknowledge that this base has some flexibility. So it could actually peel up, right, and some amount. And then, of course, we would have a bolt that was facing some tension here, but then this bolt wouldn't be facing any tension because, or would be facing less, because this is actually like the cross section that we would see of this flange right here would actually be peeling up some. So this part would be in compression, and this bolt would be handling the tension, and we would actually like balance out, I think, the areas between there. So this is sort of greatly exaggerated right there, because it could be a lot of bolts, by the way, that are taking place. So I should actually put 2 of them there, right there. Boom and boom. Of course, this missing area right here. But we would figure out this line right here would be located at where the area centroid would be of this. And then, so this right here would take up a amount of compression load that would be equivalent to the tension load that's right here, that would create the moment, right? So that's how the moment is distributed between this bolt tension and then this compression. They would form a couple, and they would equal the moment that we would have because of this force. And then another way that we could also have it, and that we didn't, in that part, we didn't like establish what the squishiness was of this. We were just saying that there's, and remember that this is like infinitely small. There is not a gap that opens up, but that's what the idea was, that we would have this. And by the way, with some preload, we would eventually make this, if we start thinking in those terms, if we don't incorporate freeload, we were taking and saying that these areas were going to match each other right here to find that center of motion onto the thing, and using this center instead of this center. But if we do start to incorporate preload, we would have like a squishiness to it, right? So it would start to uncompress right here, and it would be uncompressing more on the top than it would on the bottom. And so now we are we're having a distribution of these, and of course it already has preload onto the thing, but there's going to be like a C now that we're going to apply to the thing, right? Which was just like what we had, the K of the bolts and the K of the member plus the K of the bolts right here. So the load that would be incorporated right here would be whatever the external load that would be due to this section right here, let's just call it P, for instance, would be, the actual load of the bolt, would be equal to C times B plus Fi, right? So it still has preload, but the member uncompressing now in this concept, this is the same thing as the flange from the previous class. So I thought that was like an interesting and necessary way, not necessary, but an interesting additional piece of information on this kind of scenario of these ideas of trying to distribute forces in a section. And this is one of our most challenging aspects as engineers, when mechanical engineers dealing with solid mechanics problems, is trying to figure out what the appropriate loads are. So which one of these is correct? That's a good question. I don't know. That's not necessarily, is there going to be an answer? We could run an FEA on this, and that would definitely give us more information, but it wouldn't necessarily say that that's exactly how the bolts are loaded. It's an interesting problem, an interesting dilemma. I don't know. I'd like to see some more work done on this type of thing, or I'd like to see some more ideas. I bet there's some papers, maybe some textbooks that are written on this. But we could run models, and then we could also maybe try out some type of test rig where we built something like this, and we could put like strain gauges onto the bolts, and we could put maybe some type of pressure sensitive material inside the joint right here, and it would be an interesting thing to work through. I don't know how. I'd like to see that. And that might be actually a pretty cool capstone. I don't know. Depending on how detailed you could get, how good your instrumentation could be, and then do it for a wide variety, and do the different simulations, the different hand calculations, and maybe try to break them break a couple of bolts that way. It'll be kind of interesting. So this is also another problem from a different book, and I have I've presented way too many examples in this chapter. Maybe I will record this, but I'm running out of time. I owe a lot of people a lot of things, so we'll see what happens with that. So this is an extra example that I found interesting, and I'll talk about it in another lecture. But this is from, I think, Juvenal. It's got a very strange name. Sounds like a juvenile delinquent, doesn't it? Where we have an off-center load that's onto this piece, and we want to try to figure out what kind of loading is on each of the bolts. And I think I do it a little bit of a different way than he does. But there's this is like a combination of this type of dilemma and the one that we have previously. So that's it for this lecture. It's way too long. And I will discard all this nonsense and end this long video, 35 minutes long.